Glory, glory, hallelujah. Teacher hit me with a ruler. I cracked her in the bean with a frozen Jimmy Dean, and she ain't my teacher no more because she's dead.
All right, everybody, welcome to Chapter 7-1. In Chapter 7, we're going to talk about exponents and logarithms, and exponential and logarithmic functions. Today we're going to talk specifically about a kind of exponential function, and we're going to deal with exponential growth and exponential decay. Some of you guys may have talked some about this in your science classes before, as far as like half-lives maybe, or the growth of a population. Sometimes it comes up there. So big deal here is that we're going to represent the general form, y equals abx. Okay, b is a positive number other than 1. And so this is the general form for an exponential function. A can't be equal to 0. That's right there. B is greater than 1, or b is greater than 0, but not equal to 1. Okay. So the b base is the constant. The exponent is the independent variable with the domain, the set of real numbers. So if we just look at what the graph of these looks like, a table of values is a really easy way to do this. So we have y equals 2x, and then you just we put some numbers in here. We got some numbers out. We put some more numbers in here. We got some numbers out, and we see that our graph goes from really, really small to really, really big. Okay, pretty simple stuff there. If you could please take a second and graph each of these functions. Okay, graph each of these exponential functions. Pause the video here and graph. All right, you're back. I've tried to color code my answers here for you a little bit so you can see the difference between A, B, and C. Hopefully you got the same things just by picking some numbers for x. I picked -1, 0, 1. You could pick 2, -2, just so you have enough to get the general shape. Part D asks us what generalizations we can make about the domain, range, and y-intercepts of these functions. The domain, I think the generalization that we can make there, it's going forever in both directions. So this, the domain is all reals. The range, it looks like, if you look at the way the graph turns here, it's never going to actually touch 0. So the range is, it's just y is greater than 0, okay? Range is y is greater than 0. And then as far as the y-intercept goes, it appears, just based on these, that the y-intercept is the a value. Okay, y-intercept equals the a value. And we noticed that right here on part C, it was 2, so that was 2. Here, the a value is 1. We don't write it, but it was 1. And here again, 1. We don't write it, but there it is. Okay? Let's get all this stuff out of our way. All right, so two types of exponential behavior are exponential growth and exponential decay. For exponential growth, as the value of x increases, the value of y increases. For exponential decay, the exact opposite happens. The exponential functions shown here are asymptotic to the x-axis. An asymptote is a line that a graph approaches as x or y increases in absolute value. So the asymptote is the x-axis. It's going to approach it, but never actually touch it. There's nothing that we could put in for x that would give us a 0. If you go back to any of the examples from Got It number 1, there's nothing you can put in for x that's going to give you a 0 value. Okay. For the function y equals ab to the x, if a is greater than 0 and b is greater than 1, the function represents exponential growth. If a is greater than 0 and b is in between 0 and 1, it represents exponential decay. In either case, the y-intercept is the a value, the domain is all real numbers, and the asymptote is y equals 1, also known as the x-axis, and the range is y is greater than 0. Okay, so let's look at what this really looks like in a problem. So here we have identify each function or situation as an example of exponential growth or decay, and then what's the y-intercept? Because this number is in between 0 and 1, it's decay, and the y-intercept is 12. On part B, This is bigger than 1, so it's growth, and the y-intercept is 0.25. That's no problem. Part C says you put $1,000 into a college savings account for 4 years. The account pays 5% interest annually. The amount of money in the bank grows by 5% annually. It represents exponential growth because it's growing. This is more than 1. And the y-intercept is 1,000. That's where you started. Okay, so we can do the same thing from a word problem. Forgot it too. Take a second and try that. Parts A, B, and C. This shouldn't take you very long. Look at those. Tell me, is it growth, decay, and then what's the y-intercept? Growth or decay, and then what is the y-intercept? Ready, set, go. All right, you've unpaused. Hopefully you got for A that this is growth, and the y-intercept is 3. Hopefully you got here that this is decay, and the y-intercept is 11. And hopefully here you got that this is growth, and the y-intercept is 2,000. Okay, questions on those, make sure you write something down so we can talk about it in class. For exponential growth, y equals ab to the x with b is greater than 1. The value for b is known as the growth factor. It's a quantity that exhibits exponential growth increases by a constant percentage each time period. The percentage r, written as a decimal, is the rate of increase for the growth. So b equals 1 plus r. So it'll make sense here in a second because we're going to get into some word problems. For exponential decay, b is the decay factor. So not a big, duh moment right here. Decay factor, growth factor. The rate of decay, usually a rate of decay is expressed as a negative quantity, so b equals 1 plus r. All right? Let's take a look at what this really looks like, okay? We can model exponential decay or growth with this function right here, okay? This function right here. The capital A is the amount after t time periods. The r is the rate of growth or rate of decay, depending on is it growing money or losing money or growing in some form. The exponent t is the number of time periods, and the a right here is the initial amount. Okay, so let's look at what this looks like in a real problem. So modeling exponential growth, we've invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will be in the account after 6 years? To determine if an exponential function is a reasonable model. So the money grows at a fixed rate of 5% a year. This is an exponential model. Okay, we define the variables. So how much time? So t is the number of years since the money was invested. Well, it tells us that that's 6. A of t is the amount in the account after each year. A reasonable model is this model we just looked at. So a of t equals a times the quantity 1 plus r to the t. So use the model to solve the problem. We put the number of years here, the starting amount here, the growth rate here. That 6 that we plugged in right here is the exponent there. Then we just follow order of operations, and we get $1,340.10 after 6 years. So you made $340.10. Okay, this is how banking works, guys. This is as real as it gets. Suppose you invest $500 in a savings account that pays 3.5% annual interest. How much will be in the account after 5 years? Do me a favor. Pause the video. Find out how rich you're going to be. Okay, pause the video here. Find out how much money you'll have after 5 years. Go ahead and do that now. All right, you've unpaused. Hopefully you got big dollar amount here. Big money, big money. $593.84. If you didn't, try again. Follow the formula. If you still don't, make sure you make note of it, and we'll go over it in class. Okay. Suppose you invest $1,000 in a savings account, pays 5% annual interest. If you make no additional deposits or withdrawals, how many years will it take for the account to grow to at least $1,500? Okay, so we're going to look at a little bit at what we can do in our calculator with this problem. We let t be the number of years again, number of years, not years. We have 1,000, we have 1 plus the growth rate, which is 0.05. The t is what we don't know, but we know the amount we want to get to is 1,500. Okay, so we put this in our table, and we look real quick, and we see that it reaches it here at 9. So after 9 years, that's when the balance will be over 1,500. Not very difficult stuff, okay, using the table feature in your calculator. Go ahead and try 4A. Suppose you invest $500, and it pays 3.5%, and you want to know how many years to get to $650. And then we're also going to use the table in problem 4 to determine when that account will contain at least $1,650, okay? So right here, and please explain, okay? So go ahead and do both those A and B. Go ahead and do that now. All right, you've unpaused. The answer to 4A, hopefully you got 8 years. 4B wasn't really that difficult. Here we have 1,630, and they want to know when we're going to get to 1,650. It jumped $77 last year, so if it jumps that amount or more, we'll be up there. So 11 years, okay, is when that account will contain at least $1,650. All right, you could also just put it in your table and do it again and see it live and in action. So exponential functions are often discrete. In problem 4, interest is only paid once a year. So the one we just looked at, a discrete function, remember, is one that's not continuous. There's no connection because the interest is only calculated every year. So t is 1, 2, 3. We're not going to have a 1.5 and all these kinds of things. To model a discrete situation using an exponential function of the form y equals abx, you need to find the growth or decay factor. Okay? If you know the y values for 2 consecutive x values, you can find the rate of change, which is r, and then find b using r. So it looks like this. y2 minus y1 over y1, and then b equals 1 plus that rate. Okay, so we'll look at how we're going to use that right here with this big scary lynx. So we're writing an exponential function. So the table shows the world population of the Iberian lynx in 2003 and in 2004. The table is right here. That's the table we're talking about. Okay. What happens is if this trend continues and the population is decreasing exponentially, how many Iberian lynx will there be in 2014? So we're going to find that out. So we define the variables. X is the number of lynx, number of years since 2003, and Y is the population of the Iberian lynx, and we need to figure out the R. So we take Y2 minus Y1, so this is Y2 minus Y1, and then we divide it by Y1. So the growth rate here, or the decay rate, is negative 0.2. So then B, okay, we use that R to determine B. B is 1 plus R, or in this case 1 minus 0.2. So it's 0.8. And then we write the model, okay? The model is y equals abx. So y is 150. A right here is what we're looking for right now. 0.8 is the rate, and then we're using x equals 0 to find the initial value. So we put that in for 0, we solve for A, and we get A is 150. So now we have our A, we have our B, we can write the model. We can now use this to predict all sorts of things, okay? We want to know what will it be in 2014? Well, this was 2003. So 2003, the difference from 2003 to 2014 is 11 years. We put 11 in for the X, and we get about 13, okay? There'll be 13 Iberian lynx in the wild in 2014, okay? Seems like a lot. It's not really. Okay, it's not really. For the model in problem 5, what will be the world population of Iberian lynx in 2020? So to do that, you're simply going to take 2020, subtract it from 2003, raise it to that exponent, tell me what you get. Got it, number 5, tell me what you get. All right, for you animal lovers out there, this is a sad fact here, about 3. Okay, if it continues, there'll be about 3 left in the world, living in the wild. If we graphed the model in problem 5, would it ever cross the x-axis? Would it ever cross the x-axis? So think about it. Would it ever cross the x-axis? And we said no. Okay, remember, the x-axis is an asymptote. So it's never going to cross. That's some nice handwriting there. So it's never going to touch the x-axis, theoretically. But I suppose if there's nothing left, there would be none. But the model is never going to cross the x-axis. That's it for the notes. There should be some questions, guys. This stuff isn't easy. So share these, tweet them, like the video, do something, help a classmate so they can come prepared also. I will see you guys in class next time. Bye.